Well, good afternoon. Hope everyone had a good lunch. So first, thank you, the organizers, for the invitation. It's great to be here. My name's Stephen Walborn. You can call me Steve or Stephen. Either is fine. Yeah, so I'm at the Universidad de Concepción right now. Before before we talk about physics or photons or whatever, I just want to tell you a little bit about myself. So, okay, that worked. So I'm from the United States originally. I did my undergraduate degree at Reed College, I guess, wow, a long time ago. But then I did something maybe not so conventional. I went to Brazil to do a master's degree and then stayed on to do a PhD. So it's at UFMG in Belo Horizonte. Is anybody here from UFMG? No? Okay. Yeah, so I did a master's and PhD, and why did so I originally went to do a master's. I ended up having a really great advisor who was Carlos Monking, and right around 98, 2000 was when quantum information was really kind of starting to blossom, so it was a really fun time to be in a quantum optics laboratory, which I was working in. And like I said, I had a great advisor, exciting research topic. I was also Monking's first PhD student, or first graduate student, and so I was sort of like involved in a lot of things in the lab because I was the first student, so I decided to stay. I was finally also speaking Portuguese. At least I could order, bread, a drink, or whatever I had to do. So I stayed. Then, so 6 years wasn't enough in Brazil. I went to Rio afterwards to do a postdoc with Paulo Souto Ribeiro and also Luiz Davidovich at UFRJ. Is anybody here from UFRJ? Yes, as a postdoc. Then I got, I don't know if this is a delay or... Okay, then I got a position as a professor for, 12 years. And in 2019, kind of as the funding situation in Brazil was pretty bad and so on, and also my wife is a scientist and her funding situation was even worse. So we went to Chile, and so I became a professor at Universidad de Concepción, where I'm currently there, since then. Another thing, so I'm involved there in quantum optics, quantum information, experimental. We'll talk about that the next 3 classes. But also another thing interesting which we did in Concepción is we started a startup company called Secure Quantum. I'm not going to talk about that really at all in these classes, but I just thought I'd mention it. If you want to ask me about that during our coffee break, I'd be happy to talk about it. So it's kind of by a sequence of small miracles. It's still alive today. So a quantum startup company still alive in LATAM, with 5 years of lifetime I'm proud that we're still alive, So at the Universidad de Concepción, so this laboratory, so I should say the theoretical quantum optics has been there for over 20 years, over 25 years, I guess. But in 2006, they started a laboratory, and so Gustavo Moreira Lima, he also did his PhD. We did our graduate studies together, or in neighboring laboratories at UFMG. He went there, and he really kind of started the laboratory together. Well, Carlos Saavedra was kind of the head theoretician there, and so with his support, they started the lab. So Esteban, I guess, was Gustavo's first PhD student. He then became a professor also at UDEC. We have, so there's me, there's also Professor Aldo Delgado, who's in theory in Concepción. And then we also collaborate with some other people at other universities in Concepción. There's at least 5 universities in Concepción. And so these, Jaime Cariñe and Gabriel Saavedra are both engineers and electrical engineers, one at UDEC and one at in the Catholic University, and Gustavo Cañas is a physicist. He was also a student of Gustavo Moreira Lima, and he works at the Universidad de Bio Bio in the engineering department. Sorry, he's in the physics department, but most of their students come from the engineering department. So yeah, so we have a pretty good critical mass in Concepción, especially in experiment. So, okay, this is kind of an outline. So now you know who I am. I want to tell you a little bit about the course. So these are kind of the main kind of outlines of the 3 lectures. Today I'm going to talk about a little bit about the basics, history, concepts of quantum information processing with photons, right? Then the second lecture will be more about, let's say, current photonic quantum information processing with photons, in particular in optical fibers and with space division multiplexing, which is something we work on a lot in Concepcion. And I'll tell you in the final lecture, kind of continue the second lecture and tell you about some interesting experiments that you can do with this type of technology. So I'll go from, say, like very kind of basic, a little bit more specific, and then say very specific at the end. And so I'll start by apologizing for today's lecture. It's a little bit of a Frankenstein, so it's pieced together with some other stuff. It was basically, since I arrived all day yesterday and today, I was changing a little bit, given what I saw in other lectures and stuff. I didn't want to say repeat too much. I also saw some things I should add, and so on. So yeah, so bear with me today. I'll cover a couple topics, but the idea is to kind of give like a more general overview, and especially from a more like historical and conceptual point of view, and then we'll get a little more specific in the next lecture. So next lectures will be more state-of-the-art than this first one. Okay, that's the plan. So, okay, of course, we're here because we are interested in quantum information, quantum technology, and processing information with quantum physics. So, of course, you have kind of like the three basic things you have to do, right? You have to have some sort of quantum state, so somewhere, some physical system where you're going to encode information, so coherent information, quantum information. And so you need at least, say, 2 different orthogonal levels. You could also have additional levels and maybe do some higher dimensional information processing. Well, this would be for, I mean, if it's a single qubit, in general, you have many, many levels, right? You have to then do some sort of operations, which are unitary operators acting on this physical system. And then you have to have some mechanism that lets you get information, classical information out, so you have to do some sort of measurements. And of course, there's this fairly well-known DiVincenzo criteria, which has kind of, I guess, 7 specifications of that every quantum information processing platform should have in order for this to happen, right? So you can look that up. We won't talk about it here. So this is the main thing. So what I want to show you now in the first part of the lecture today is, so how can we do this with light, right? What are different ways that we can encode quantum information in such a way that I can then process it in some way by doing some operations and then measure it and so on. Why are we interested in light? I know there's a message here on the computer saying unable to establish secure connection to Zoom. I guess that's okay. Does anyone know? Okay, whatever. Okay, so why are we interested in photons? Well, I mean, there's many different platforms for quantum information processing. We've heard a lot about them. I mean, I've been here since yesterday. I've heard a lot about them. You've heard about even more. But photons or light in general will definitely play a part because these are, your mobile qubits, your flying qubits is how you can transport information from one place to another. So you can, say, encode information in light or in photons and send them somewhere else and measure them, and that's great. Or you might actually entangle different systems, as Danielle Fenlinto was talking about yesterday, via some light or some photons that are emitted by these systems. You do a joint measurement and you can entangle them. So in any way you cut it, you're going to need photons. You're going to have to be able to manipulate, measure, and do some at least basic processing and with light or with photons. So light is quite interesting, because you have many different degrees of freedom to choose from, which we'll talk about quite a bit today. And of course, you can even have higher dimensional encoding, which is also something that's advantageous, sometimes advantageous, sometimes not. We'll also get into that a little bit. Well, here's already going into a little bit more. Of course, like doing some sort of higher dimensional encoding, it can be interesting, for example, or even sometimes essential. For example, in quantum textuality, that's just a phenomenon you can only observe in 3-dimensional systems or higher, right? There's some also advantages in observing, say, quantum non-locality, which you can then use to do quantum key distribution. And so if you have higher dimensional systems, you can, say, lower the detection thresholds for secure bit rate and so on in QKD, and also in Bell inequality violation and so on. So there is some advantage for these higher dimensional systems, and light gives you this possibility. And of course, one thing we'll get into really in the second and third, well, mostly in the second lecture, is that of course, we want to take advantage of all of the technology and the current state of the art and the ongoing development of telecommunications, integrated photonics, and all of this stuff in the system. So, and we want to follow the trends in those fields. So I saw this, this graphic the other day. It's of, say, like the field of, say, of quantum information, of companies that work in quantum information technology. So I don't know, I can't really, maybe, I don't know if you can read these titles or not, but you have, the point I want to make by showing this here is that I would say most of these companies have something to do with light and with photons and so on. I mean, quantum cryptography, of course, you have to send photons or light from Alice and Bob to do QKD. You have photon detection and counting. Of course, this has to do with light and interaction with light. Photon integrated circuits and photonics, IP, which I guess is information processing. You have photonic quantum computers, your PsiQuantum, Quandela, which Danielle mentioned yesterday, and so on. So you have, I mean, a good part of these companies have something to do with photonics. So this is kind of beating home the point that, you know, photons and light are essential for quantum information. Okay, so how do we do this? So from, like, say, historical or most basic concepts. So you could, like, starting from the upper level, there's kind of two different ways to encode information or say quantum information to light, two approaches, right? So the first approach, which I will only really talk about in this slide, but we did hear a little bit about this morning in Michel Brun's talk, is what is called, say, continuous variable quantum information. So here you have intense fields. So these are modes of electromagnetic field. They're populated with photons. So you have some states, quantum states, or whatever, what have you. You can describe these fields using quadrature operators or the field operators, A and A dagger, and so on. When you write this and work with this in terms of the quadrature operators, you have this nice detection scheme, which is called homodyne detection, which allows you to measure expectation values of the quadrature operators. And you can actually formulate almost everything you can work with, say, the conventional qubits, you can formulate in terms of these quadrature operators, and you can do all sorts of quantum information protocols. Here, as we saw this morning, you can talk about the quantum state of light which you're producing using different quasi-probability distributions, such as the Wigner function, for example. And so here's what a Wigner function of a squeeze state looks like. So it's something, you're not going to write down a density matrix, you're going to calculate a Wigner function and try to measure it or study it or whatever you have for you. What's really interesting about this type of approach of continuous variable photonic quantum information is that it's deterministic. And so this will maybe make more sense in a little while. The point is that when you're generating the field and you go to measure it, you always have a result. So you're not doing any post-selection. So there's nothing probabilistic when you generate and measure the fields. So that was something that's always listed as an advantage of this type of approach, right? And that'll be a little bit more clear in a minute. So here, through say 20 years of papers and research, it's been shown that you have this type of approach gives you a full quantum information processing platform. If you can do, say, squeezing, so that's having nonlinear media in a cavity, so you can make squeeze states. You can do different displacements, which is applying lasers and so on to your field. You can do homodyne detection, and then so all of this stuff, these first three here, are what are known as, say, Gaussian operations. So if you have, say, a Gaussian Wigner function like this one is here, and you apply these first three things, you'll always have some sort of Gaussian function here. And it's known that that's not sufficient to do universal computation. So you have to have some sort of non-Gaussian operation here, which typically is photon number detection or some sort of cubic phase gate. So the point is you have things here which are fairly, I don't say they're easy. Carla will say doing squeezing is not easy at all, but I mean, it's something we understand how to do, and then you have to add some, say, different ingredient, which could be, say, detection on the photon number basis or some other more complicated operation. So this is an approach which we're not going to talk about. There's several books written on the subject. There's some nice review papers, and so I suggest you to look there if you're more interested. The other approach, of course, is the not discrete method, is the discrete variable, or here, if you want to think of it better, it's finite state space. So here, we're going to have, say, single photons or fixed photon number states. So I'm going to have, say, as Danielle mentioned yesterday, these sources of single photons. I'm going to take these photons and put them in different interferometers or waveguides or whatever, and make them interfere and so on. And so here I'm going to not only produce single photon or fixed photon number states, but I'm also going to detect them, right? So I have to have at least single photon detectors, or even better yet, if I can do photon number detection, that's even better, and that's something which exists nowadays. Now, this type of scheme is typically probabilistic in the sense that if I do and in this case, this is bad, but it can also be good, because so if I produce, say, n photons and send them to some sort of optical circuit to do some computation, then I can look for some signature of n photons at the end. If I detect all n of them, I know that, okay, it must have been unitary, I didn't lose any photons along the way, I eliminate the losses. It's going to be, sometimes it might not work, but I'm going to see those n photons, I'm going to have some sort of result of my calculation or whatever it is, right? So that's say bad, because sometimes it won't work, right? It might only work, once every million of times I try, but okay. On the other hand, I don't have to worry about losses, right? Losses is just going to be efficiency. It's not going to, the loss isn't going to affect the quality of my state. So the previous approach, the continuous variable approach, it's deterministic in the sense you're always measuring something, but losses are basically going to take your quantum state, like that squeeze-Wigner function which I showed, and it's going to basically make it closer and closer and closer to a vacuum state. I mean, if you would lose all your photons in your field, you would have the vacuum. So, so it's kind of there's this trade-off, right? So okay, I put this here. I'm not trying to make say one is better than the other or negative, positive, whatever. It's just something that has to be taken into account. So this type of scheme. So again, you have a full quantum information processing platform if you have some basic elements, which also Danielle mentioned a little bit yesterday. So if you can do, say, linear optics, which we'll talk quite a bit about today, if you can kind of produce these single photon states or n photon states on demand, that allows you to do some more advanced operations. And then, of course, you need to have, say, good detectors, so good single photon detectors, or even better yet, photon number detection. And then you have to do some tricks like feed forward of measurement results and so on, and we'll mention that a little bit. In terms of the single photon sources, so I'll talk a little bit today about spontaneous parametric down conversion, which is kind of historically this important source of entangled photons. It's also what goes inside your cavity when you do squeezing, or when you produce squeeze states. A sister process is spontaneous four-wave mixing, which is more or less the same thing, but you have, say, 4 fields instead of 3. So those I'll mention, or SPDC I'll mention a little bit today. Danielle yesterday mentioned, say, single emitters, like these nano emitters and so on, like quantum dots, nano vacancies in diamond and other materials. And so ions, atoms, so there are several lectures that are talking about this sort of thing, so I'm not going to mention them. But these, of course, are the kind of gold standard in terms of sources. So eventually, I mean, these SPDC sources, which we'll mention today, have been great for 25 years, but eventually they will be replaced by these single photon emitters, which can all give you, say, single photons on demand or something fairly close to it. So that's where, like, the field will be going. Okay, so this is the approach which we're going to talk about today. And in fact, all 3 days. And so just to start from like the square one, right? So this, I'm sure you've seen this several times during the lectures. This Michel Brun also mentioned. When you quantize the electromagnetic field, right? So you have the classical field up here, or one of the components, and you quantize these complex amplitudes into field operators, and so you have your famous A and A dagger, which don't commute, and then you have this this operator here now, which is your electric field operator, and so these A and A dagger enter here. So these are like the kind of the Fourier transform of these field operators, and of course you have this whole harmonic oscillator-like space where you can apply A dagger to some. So this N is a Fock state, an N photon state. When you apply a dagger, you add a photon and you have some coefficient. When you apply A, you destroy a photon and you have some coefficient. And so these quantum states here. So a single photon state is described as this, and an n photon state then would be described as something like this. And so here I didn't write it, and I apologize. This A dagger here is going to create a photon in the mode, right, that's defined up here by these indices K and S. So here in this is an expansion plane waves. So these are creation operators into, say, a plane wave mode. So a spatial mode that's a plane wave with some well-defined frequency, which is given by the modulus of K, and then S is the polarization, right? So you're always creating, when we do this, we always think of creating a photon in a mode, right? So this is, so of course, like a large part of quantum optics is saying, okay, I have, say, a single photon state that's input to some device, and so I can calculate what's going on, and we'll do this in a minute or two, or in a little while. I can calculate what's going on by seeing how these operators kind of evolve through my circuit and then apply it to vacuum, and that's a great way to do the calculation. But there's also a notation which is maybe an abusive notation, but it's so common we have to mention it, which is just writing a single photon state like this, right? So this is a shorthand notation, like write a state psi. And so in many cases when we write this to refer to a single photon, we're saying, okay, this state psi is a single photon in some mode, which is the mode of interest. So it might be like psi might be a polarization state of the photon. But of course, every photon has spectral properties, spatial properties, and so on. And so when I write this and I don't say anything about the spatial or spectral part, and psi refers to polarization, I'm basically saying, okay, the spectral spatial part is constant, it's not evolving, I'm not manipulating it, it's just kind of along for the ride. And so let's just not bother writing it down, but it's always there. Of course, if you really want to be, let's say, formal, you can write, you of course have, say, this kind of abbreviated state, and you have, vacuum in all the possible other modes that the photon could possibly occupy, which I think we're all pretty comfortable in ignoring that. We only write down the modes which we're using, right? So, of course, that's really common. So I'll abuse the notation a little bit today. Sometimes I'll write something like this. I think it'll be really apparent when I'm using one or the other. Sometimes I'll write something like this, and then sometimes I'll use the previous notation with AA dagger and Fox states and write the mode in terms of the ket, okay? So, so you see, so of course, if you, I'm sure you've read many papers in which they use kind of both notations, and you can switch back and forth in between one and the other, depending on what's more convenient. Okay, so let's talk about how can you encode information into light or into single photon state. So of course, the canonical example is through the polarization, which I already mentioned. So I can basically, as it said on the slide, the previous slide, a single photon has, or the mode structure of a single photon is the same as the classical electromagnetic field. So I can manipulate the polarization or whatever of a single photon. It's a two-level system, just like the polarization of light. I can have it's a two-dimensional vector, right? So I have all the same kind of classical polarization states. I can make a single photon that has the same kind of polarization state. So linear polarization, circular, elliptical, whatever. You can just define, say, like a computational basis. If you want to kind of put this in quantum information terms, typically it might be horizontal and vertical, and you can write them as 2D vectors. And so the interesting thing about polarization, what makes it so useful, right, is that you can, the rest of so the encoding is quite easy. You see this in many quantum mechanics textbooks when you talk about kind of the basic ideas of quantum information, interferometers, and so on. But then you can process, or you can do the rotations and the unitary operations on polarization using really common elements, which you can buy in a catalog. You can buy from Thor Labs or other companies. You have really good high-quality measurement devices, which are polarizers or polarizing beam splitters. So it's a really good system to work with. It's cheap and conceptually easy to understand. The only downside of this maybe is when you go into optical fibers or even, say, some sort of waveguides and so on, then you have effects like dispersion, you have birefringence, which you might not want, so you have to kind of compensate for those sorts of things. But the good news is typically you can compensate for them, and it's all within the realm of, say, classical optics, but so it's pretty well understood. So just to mention, in case you've never seen this before, what is a wave plate? So these elements that do these operations. So wave plate is just a slab of material with some thickness L. And so the point is, if you have this device oriented at some angle. So there's two axes of symmetry in this device, right? A fast axis and a slow axis. And so if you have the device oriented at some angle theta, you're going to apply basically a phase difference between the polarization that is parallel to the fast axis and the polarization that would be parallel to the slow axis. So if this is some arbitrary angle theta, what you're going to end up doing is kind of rotating the polarization in some way. That's going to depend on, well, the index of refraction of the material, the thickness, and this angle. So, the general form of this linear retarded, this wave plate, is given by this. So it's just basically this diagonal matrix giving this relative phase rotated to this basis, right? And so with this, you can do a lot of things because you have several parameters here. You have, well, here that appears in the matrix. You have delta, the phase difference, and you have the angle theta. So you can play around with this a lot, and you can make these single qubit gates. So the most common one, or the two most common ones, are the half wave plate. Here, this is when the delay is equal to pi, so a half wave. And so the general matrix for the half wave plate is this. You can see it's similar to a rotation matrix. It's actually a reflection matrix. And so some special cases, if you choose theta equals 0, you see have a matrix that looks like this. So you might recognize that as like the Pauli Z gate, so Z in quantum information notation. Or if you put this at angle, the wave plate angle pi over 4, you have a Pauli X matrix, which is, of course, one of the basic rotations in which you want to do in quantum information. If you go pi over 8, you get a matrix like this, which is very similar to a Hadamard matrix, another basic operation in quantum information. So that's the half-wave plate. The quarter-wave plate looks, so when delta is equal to pi over 2 is something similar, and you can look at some special cases and so on. So the interesting thing here, and something that's well known from classical optics, or polarization optics, is that actually you can do any polarization rotation, or in other words, any unitary operation up to a phase by a sequence of 3 wave plates. So if I have a quarter wave plate followed by a half wave plate followed by another quarter wave plate with different angles, I can do any unitary. So that's like a kind of golden result, and that's what you always go to when you're writing a paper. You can say, well, I can do any unitary with these 3 wave plates, so my job is done. When you go to the lab, you see, okay, well, the wave plates don't work exactly like the matrix says, and you have to calibrate them, and it's not as easy, but in theory, you can do any unitary you want. In terms of the measurements, I mentioned you have this polarizing beam splitter, which these operate in several different physical principles. So these cube devices, which you have like a dielectric film here, which basically separates two orthogonal polarization components, such as horizontal and vertical. So of course, if you send you send an arbitrary polarization state in, you're going to get part of the light exiting here, or let's say this component exiting through the horizontal port, this component exiting through the vertical port. This is all unitary, so it's reversible, so I can even do this. I can reflect them back together and get the same output state. And so I have kind of here a little interferometer that I could play with. I could move this mirror around and change the polarization state and other stuff like that. So this is a basic element, and it's quite nice for separating the polarization components. Then you can operate on them independently. But also, of course, you can do measurements. So if I, instead of recombining the beams, I put detectors here, I'm, of course, going to get some output probabilities, which are given by the square of these amplitudes here, just like the Malus law, right? So, so this is kind of the iconical projective measurement, right, of a qubit here in polarization. So again, in the polarization optics is really well understood. You have really high quality devices that are available, and it's iconic in this sense. So over the past, say, 20 years, people have looked into other degrees of freedom of light for quantum information, and kind of what has been done is saying, okay, how can I make these same devices, but that act in these other degrees of freedom? So I want to make, wave plates for doing rotations. I want to have something like a polarizing beam splitter, which lets me separate 2 components and measure them, and so on. So these are really kind of iconic in that sense. So for example, one approach is with transverse spatial modes. So these are the eigenmodes of a resonator, or even of, say, pre-propagation if you allow the width to change. So these would be, say, the Laguerre-Gaussian modes, which are famous because they have angular momentum, which is given by this L value here. So you have these, what are known as donut modes, right? So these are all orthogonal. So here, just if I could produce and manipulate within this state of modes here, I could have 16-dimensional space if I wanted to. You also have another basis known as the Hermite-Gaussian modes, which are similar to these. So these, of course, would appear if you work, if you do, say, if you work in, say, cylindrical coordinates, right? Because you have kind of azimuthal symmetry here, right? So you can write these really well in cylindrical coordinates. This is what happens, or these were the same modes, or let's say, these are similar modes, but when you work in Cartesian coordinates. So these modes here are superpositions or linear combinations of these modes here, and vice versa, and so on. So you have this kind of correspondence between these two bases, and you can do a lot of things with this. Yeah, so these are solutions of the paradoxical wave equation. In terms of generating them, you can use holograms. You can generate them directly in a laser cavity. You have what are known as mode converters, which convert between one basis and the other. So these are cylindrical lenses that basically, so for example, if I would take this L equal 1, P equals 0 mode and send it through this mode converter, which is some cylindrical lenses, I convert this mode into some combination of I could convert this mode into, say, this mode or this mode, depending on how I orient the lenses. So you can kind of do these transformations and so on. Something that's also interesting is, so when you go to optical fibers, and we'll talk about this in the next lecture, especially structured optical fibers, you have similar looking modes that also appear there, which of course give you the same thing. So if these form, say, orthogonal bases, I can encode information in them, and so I can also do the same thing with these similar modes in the fiber. So I wanted to show you this, let me see if this will work. So this, when I was a student in Belo Horizonte, one thing we did was we produced these modes by opening up the laser cavity and putting a wire inside. And so this is a video, which I'm going to turn down the sound. I don't remember what we were talking about when we made it. But so if this works. So here what we're doing, yeah. So we're scanning the wire across the front of the laser. So scanning the wire this direction, the laser cavity. And basically, when the wire is outside the cavity, like in the image down here, you have this Gaussian mode. So it's as though the wire is not even there. When I start to bring the wire this way into the cavity, I basically interrupt the generation of the Gaussian mode. And so the laser wants to always operate in the lowest order mode, which is the lowest amount of energy necessary to produce this mode. So it's going to produce the mode that has a nodal line, or basically a zero intensity, exactly at the position of the wire. So here we are able to generate these two different modes, right? So one mode such that it has a nodal line at this position of the wire, one mode when the wire is in the center. Oops, sorry. I wanted to play the video again. And then the same mode again when the wire is over here. And then when the wire is out, we get this other mode. So I wanted to show you this because this is something that when I was a student, I spent hours scanning the wire back and forth trying to make different modes, and it was quite fun. Okay, so how can you manipulate these modes? As I mentioned, you want to have wave plates, so you can, in addition to these mode converters, well, I'll show you in a second, you can actually rotate the mode, so I can take one of these Hermite-Gaussian modes, send it through this dove prism, and I can rotate it to another one. So that's like a half wave plate. I can do this mode converter, which I mentioned, which is like a quarter wave plate, transferring a Hermite-Gaussian to a Laguerre-Gaussian. And then here you see, here's how I would do, say, like the polarizing beam splitter. I have to interfere, I have to interfere a mode with the reflection of itself, right? So here basically, this is an interferometer. These are regular beam splitters, so when I have some superposition of modes here, I come into the interferometer, part of the light goes to one path, the other half of the light goes to the other path, and then when I interfere them, basically because here I have 1, 2, 3 reflections, and here I have 2 reflections, you're going to interfere a mode with the mirror image of itself. So then it depends, what's the parity of this mode? And so, as it turns out, these modes have, one is even and one is odd parity, so you can separate them. So this is just like the polarizing beam splitter. And so you see this is quite a bit more complicated than the polarizing beam splitter. It's a whole interferometer. And this is what you would do maybe, I don't know, I guess you would still do this nowadays, but there's definitely more intelligent ways to do this, but this was kind of the first idea from 20 years ago. Okay, so transverse modes, so I should mention this is something people work on a lot. Not so much in integrated optics, but as I mentioned, in optical fibers, you have this type of mode structure as well. In free space propagation, so for example, in the quantum Rio network, which Danielle mentioned yesterday, one of the links is through free space, and they're going to try to use these transverse modes to send information from UFI across the Guanabara Bay to the CBPF. So another type of encoding is what's known as time bin. So here, basically, so you can imagine I take, say, a laser, or I take light, and I make it, and I pulse my source, right? So I have kind of two time slots, one here at 0 and one with a delay minus delta. And so I can do this in such a way, so if I can have a single photon source that I can kind of pulse in this way, I can make it such that my photon either appears in time slot 0 or appears in time slot 1. So it's, of course, in principle, only in one of them. Of course, I could make it in a superposition of these different time slots and so on. So this situation up here, I can call my 0 state. This situation down here, I can call my 1 state. And yeah, so this is another way to encode information. Of course, I could have multiple time slots, so I could go up to a dimension kind of whatever I wanted to, until I got tired of waiting around for the photon, essentially. And yeah, here, of course, I can make, if I can produce these states in my computational basis, I could make superposition states using some of these devices which we talked about before. So I could construct something that makes me an arbitrary superposition. I could do an analysis, and I could make like the beam splitter to do this analysis. Again, doing interference of the state with itself, putting a delay, and so on. So this type of encoding is also widely used. It's quite nice for single mode fibers, where basically because these time slots are very close together, so perturbations and so on the fiber are going to affect the two time slots equally. So it's fairly robust in terms of the relative phase and so on. So it's again something that's widely used. Now this is the final approach, which actually we'll probably talk about the most in the next 3 days. So this is what's known as momentum or path encoding. So here's very similar to the time slots. Just now I'm going to have two propagation directions. So you might think I have two optical fibers. I can have my photon in the red fiber, or I could have the photon in the blue fiber. So one photon in red fiber, 0 photon in blue fiber, or vice versa. So that's my computational basis 0 and 1. So of course, when you go to integrated photonics, waveguides and so on, this is kind of the encoding scheme which you're going to use. So this is kind of actually really studied, say, in terms of theory also, because there's this nice result that shows that you can perform, as we had the arbitrary unitary for polarization with the quarter wave plate and the half wave plate, here you have the same thing, but with two similar devices. One is a phase shifter, so basically if I have some material that puts an arbitrary phase on one of the modes but not the other, that's the one device I need. And then the other device I need is a beam splitter that has, in principle, variable transmissivity. So basically, if I can adjust how much, so the beam splitter operation is written in terms of these states, right? So 0 is here the state that comes in red, right? 1 would be the state that comes in here in blue. So basically, if I can adjust the transmission coefficients of this beam splitter such that the red photon would split with these sorts of coefficients here, then, so if I can do these two devices, I can do any device. So I can cascade these and so on and do kind of any unitary. And we'll see this in more detail in a minute. So this is great because if you want to propose experiments and so on, you can basically break everything down to phase shifters and beam splitters, and then eventually when you're doing an experiment, you have to think, okay, how do I do this? But at least from concept, it's really nice. It also gives you a nice way to do like an accounting of resources. So how many beam splitters, phase shifters do I need to do something versus how many beam splitter phase shifters with some other scheme, you can kind of put these on an equal footing. So it's like breaking it down into, say, elementary logic gates, but in this photonic encoding. Okay, so these are some options of different degrees of freedom. You can, of course, go into higher dimensions, which I mentioned with some of them, and of course, you can combine them all together. So I can basically define or devise some experiment or some scheme in which I can basically have, say, two polarization modes I can produce a photon such that it can be in one of two polarization modes, one of several transverse spatial modes, one of several linear modes, so different directions or paths of propagation. And I can also use time bin or frequency, which would be the conjugate degree of freedom here. So I can combine this all together kind of however I want. I could define a mode that's a combination of all of them and so on. So this sort of thing is done and is completely available. And a lot of these kind of little tools which I showed you are useful for doing this sort of thing. So I'm going to go back to the path encoding, the momentum encoding. So there's this nice result, which I mentioned the phase shift and the beam splitter, but there's a nice result that shows actually you can perform any unitary in this. So if I consider, say, D modes, right, I can do any unitary that transforms these modes. So this would be a D by D unitary, has D inputs and D outputs, right? I can construct this using these different architectures here, right? Where every point where these two lines cross is actually equal to this device here. So this is a Mach-Zehnder interferometer. So it's composed of two phase shifters with certain values of the phases and two beam splitters. So this device here is actually well, here it's called T, so it's a device that's a phase shifter and beam splitter together. So again, it's this basic element which we're defining. So I can construct any unitary using this particular arrangement. So of course, today in integrated quantum photonics, what you can go online, different providers, and you can order something like this. So there's two kind of schemes. One is this REC scheme, which is from way back in 1994, but also this Clements scheme, which is more recent, which is more efficient in the sense that there's a shorter optical depth. So if you say, okay, how many of these interferometers, if I have a photon coming in some arbitrary mode, how many interferometers it's going to cross? And I compare the two schemes, I'll see that this scheme is shorter. So it's, say, computationally more efficient in that sense, because every little bit of glass or whatever I propagate, I have losses and so on. So you want to keep this as short as possible. You can imagine there's millions or very, very many of these, and so of course this turns into your computational time, how long it takes the photon to traverse all of this, which of course seems kind of dumb to think about now, but if you have many of these devices, and of course this can be relevant. Loss is the real issue here, though. Yeah, so you can go online, you can buy these kinds of devices such that these phases here are controllable. So basically, if I go online and I buy this, how many modes are here? 2, 4, 6, 8, 9, is that right? So I can get a 9x9 arbitrary unitary that I can program by applying voltages and so on to these phase shifters, and I can do anything I want. So then I can, get my photon sources, I now have my programmable unitary, and then I can have my detectors. So then I can really construct anything. Yeah, so this is a really nice result. So, so when you look at these, think, okay, well done. I can build, a quantum computer because I know I can do an arbitrary unitary up to any, there's no limit technically on D, right? There might be a technological limit, but is there any fundamental limit as to how big my unitary device can be? Information processing or quantum information processing on a D by D, or on a D-dimensional system where D can be anything is a universal quantum computer, right? Of course, it's not that easy, right? This type of approach is not scalable. So if you think about this for a second, you see why. So if I want to encode, say, the equivalent of n qubits of information into these optical modes, right? Then I'm going to send single photons. That would require 2 to the n modes. So when n is small, it's not too bad. When n gets large, this, of course, grows exponentially. So here, I don't know, I guess I drew this for 4 qubits. So there's 16 modes, right? So here, of course, this applies to any degree of freedom, and I write them in terms of momentum modes. So I can imagine I have some quantum information in my photon. I'm going to kind of put this into this type of interferometer with these different momentum modes. And I say, okay, what's the physical limitation of this? And so, well, the modes should be separated by something like, at least something like the wavelength of the light, right? So they have orthogonal modes, right? That's kind of the minimum space between these modes and when I build this device. So if you do a calculation, you say, okay, I want 40 qubits, which nowadays no one is excited anymore about a computer with 40 qubits, a quantum computer. And I calculate how wide would this interferometer be. So for 40 qubits, it would be, well, 2 to the 40, and times, I don't know, maybe I took a micron for lambda here. So that gives you 1,000 kilometers. So my interferometer would be 1,000 kilometers wide. And so on, you see this is not scalable at all. And so this is an optical argument based on something which I saw in this paper here, whether you do the same calculation for, say, the different orbits of the hydrogen atom, I think. Or you can also think about this in terms of the quantum harmonic oscillator. I want to encode qubits into a single oscillator, and you see this isn't scalable, and you have, say, a similar exponential explosion of how much energy you need, and so on. So this type of approach doesn't work, right? However, there is, well, I want to say kind of two things. One thing in support of this, but then also kind of like put this in a little bit of perspective. So the other issue here is not just the size of the interferometer. It's okay, well, I also have to detect the photon, right? So, and detectors are one of the most expensive components. The best detectors nowadays, you have to have them, cool them cryogenically and so on. It's a whole thing. And so if I want to, say, encode my 40 qubits into 40 photons, suppose I can make 40 photons on demand or whatever, I would need 80 detectors. Assuming I want one detector for the 0 output, one detector for the 1 output of each photon. If I'm going to use my 40 modes, I need, well, this many detectors, so more than 1 trillion detectors. So, I mean, detectors are, you know, a set of 8 detectors is like $100,000, so I don't know how many 1 trillion would be, but it's not feasible. But on the other hand, these detectors are inefficient. Even the best ones have, say, efficiency 85%. I mean, you have to also include coupling into the detector with fiber optics, all the losses you have and so on when you have multiple photons. And so you have an efficiency that's typically, you know, much less than 1. And so your efficiency of detecting your n photons scales exponentially with n, right? So it's, you know, a number smaller than 1 to the n, it goes to 0 really quickly. On the other hand, detecting your n qubits that are encoded into a single photon, your efficiency is the detection of a single photon, right? So there must be some use for having, say, higher dimensional systems. I mean, it's not efficient for encoding, but it seems to be good in terms of, you know, of losses and inefficiency in detection. So this, and again, so this is kind of my personal take on it after working on this sort of thing for a little while, is that there's, so this, when people talk about high-dimensional encoding with single photons or high-dimensional entanglement of photons, it's really, in my opinion, it's really interesting up to, say, some reasonable number of or reasonable dimensions, say, roughly less than 10 or so. So, I mean, okay, for if I have 4 modes, I can encode 2 qubits, that's fine. If I have 8 modes, I can encode 3 qubits versus 6 modes if it were 3 photons, and so on. So there's some, the scaling is not so bad when d is small, and of course I have this efficiency gain here. So as I mentioned, this type of approach of this high dimensional thing using either multiple degrees of freedom or higher dimensional encoding in the same degree of freedom is currently an interesting approach for, say, QKD and other things where you're not really so interested in coding more information, but you want to be able to lower the detection thresholds that are necessary and what you're able to do with your detectors. So you want to basically, this is where you're going to gain an advantage as opposed to say, oh, I can encode, you know, 2 bits in a photon instead of 1. I mean, sure, but the real thing is this efficiency argument. At least for, say, you know, proof of concept experiments and being, you know, the first, you know, I don't know, the longest QKD link and things like this, right? Yeah, so the point is here, so if you really want to think about, okay, scaling photonic quantum information processing to do, you know, build a quantum computer or universal quantum computer, if you will, you really need to use multiple photons, and this is, of course, a technological challenge. So, so I wanted to mention, so again, Danielle mentioned this yesterday. I'm going to go into a little bit more detail about it today. So how do you do scalable photonic quantum computation? It's possible. There's companies pursuing this. I think the company that's received the largest amount of private investment, which is PsiQuantum, if I'm not mistaken, is pursuing this. So I showed you how you can do these single qubit gates in a number of different degrees of freedom, single qubit gates, really high quality, no problems there. The hard part here is it's well known that with these single qubit unitary operations, if I could do any 2 qubit, say, controlled gate, such as a controlled X or controlled NOT or a controlled Z, then I could build a universal quantum computer with these these primitives. So arbitrary single qubit unitaries. I can even dwindle this down into a handful of single qubit gates and a single controlled operation, and I can build a universal quantum computer. So for photons, the big question is then, well, how do you do this 2 qubit, or better yet, 2 photon gate? And of course, you need some sort of interaction between the photons. I mean, the photons don't interact, so you have to go to some tricks, right? So one of the tricks is to use 2 photon interference. So I'm sure you probably heard about this within the last week or so. I'll go through it quickly. The idea is, so this was something that was first demonstrated by Hongel and Mandel in 1987, also Shi and Ali around the same time. So the idea here is I have this beam splitter. So the beam splitter has a transmission coefficient T, right? So I've got 1 photon coming in mode A, 1 photon mode B. So my initial state using this notation now is this, where 0 is vacuum. So, so what I can do is I can say, okay, how do these field operators propagate through the beam splitter? These are what the equations look like, right? So A converts to some linear combination of C and D. B does the same. And then you can say, okay, well, what does this product AB look like now with these transformations? I'll calculate this. And then I can consider, say, specific values. Well, I can first rewrite this a little bit, and then I can consider specific values of T. So if T is equal to 1/2, so it's a 50-50 beam splitter, basically you see that, well, my initial state, which was in 1 photon A, 1 photon B, I'm going to end up with 2 photons in mode C or 2 photons in mode D when I apply these operators to the initial state. So these operators go like this, showing that I'm creating or 2 in C or 2 in D. So this is 2 photon interference, right? And this is, you can observe this, this has been observed for, I don't know, 40 years, right? So how do you use this to build these quantum gates? So yesterday was mentioned this KLM scheme, right, where they, in their abstract, they say this, right, that efficient quantum computation is possible using only beam splitters, phase shifters, single photon sources, and photodetectors, right? So Danielle mentioned yesterday that this, nowadays we know this scheme is, say, not the best one, but I'm going to show it to you here because it's, well, from a kind of a historical perspective, but also because it's just so ingenious and it's cute and so on, and it's also easy to explain versus some of the other schemes. I'll mention one of the other ones at least in the end. So, but this is kind of what, let's say, started this idea that you could actually build a quantum computer with photons, like a real device that, say, presents challenges, but not challenges that are any more outstanding when compared to other platforms. So, okay. So like picking apart what they wrote here. So beam splitters and phase shifters, we saw that already. These are just linear devices. These, you buy them on the Thor Labs webpage. Where does the nonlinearity come from, or how do you transform this information in this nonlinear way? This comes from the photo detection and pulse selection. Here they say efficient. What do they mean by that? Well, it scales polynomially in terms of the resources. That's kind of the definition of efficient in computation. And then, of course, you need these heralded single photon sources. So you need single photons on demand, which also we heard about yesterday. Also, these photodetectors that you need must be photon number resolving, at least distinguish between 0 photons, 1 photon, or 2 photons at a specific detector. Yeah, so how does this all work? So breaking it down, the first thing they did is they introduced a quantum gate, which they call the nonlinear phase shift gate. We'll see how this works, but it's probabilistic, so it's going to work with a success probability of 1/4. It's going to require ancilla modes and an ancilla photon, and the success is going to be heralded by a certain detection event, and we'll see that. I'm going to need 2 of these with 2 of these NS gates, I can build a controlled Z gate, which is what I'm trying to do here. I want to make this 2 photon controlled logic operation. But I'm going to need 2 of them, so I need them both to work. So the total success probability is going to be the product is going to be 1/16. And of course, I'm going to know when it's successful. So it's only going to happen, say, 6% of the time, but I'm going to know when that is. Of course, an important thing which they show in their paper, and which is kind of the backbone of a lot of the quantum information processing with photons, is that the fact that this is probabilistic, you can actually move this online. And this is because, Gottsman and Schwang showed, way back in 1999, that you can actually do teleportation of quantum gates. So basically, I can keep trying to realize this controlled Z gate until I know it's successful. How do I know? I detected some photons that told me I detected some photons over here that told me I implemented the CZ gate on these modes over here, and I can teleport this gate onto other photons. So this is kind of an ingenious thing because the probabilistic nature kind of goes out the door, provided I can just keep trying until it works, right? So I can bring this up to 1/2 success probability just with teleportation using what they showed back in 1999, and then you can actually make this better with, say, a more complicated procedure. So in principle, you can bring the success probability pretty close to 1, and that's kind of was what they mapped out back in 2001, and which I think is really ingenious. So how does this nonlinear phase shift gate work? So here's 3 input modes, right? Psi is going to be some arbitrary state, which is written here. So 0, 1, and 2 are Fock states. So I have a combination of 0 photons, 1 photons, or 2 0, 1, or 2 photons with some arbitrary coefficients, right? That's in this input mode here. This are going to be my ancilla. So one of my ancilla modes has 1 photon in it on demand, and the other ancilla mode is in vacuum. So I have some beam splitters with some coefficients here. So these are the transmission coefficients. And so basically, what this does, if you work it out, is that let me say this. So this works on post-selection. So if you basically propagate all these modes through these beam splitters, and you say, okay, what does the state look like when I detect 1 photon here and 0 photons here? Well, notice my input was 1 and 0 here, so I'm detecting 1 and 0 here again. That means that up here I have also some combination of what came in. So if I have 0 photons coming in here, that means I'm going to have 0 up here also. 1 coming in here, I'm going to have 1 up here. 2 coming in here, I'm going to have 2 up here. And if I have some combination of them, I'm going to have some combination, right? What's going to change are the different coefficients. And so if you propagate the state through this, you get this, where C, D, and F are these numbers here, which depend on all the different characteristics of the beam splitters. And then you can say, okay, well, this is what I want, right? This is what I got in the calculation. So I want C and D to be equal to minus F, right? And in fact, that's what you do here. And you can solve for the beam splitter coefficients, and you can find out what they are. And then, as it turns out, you can make it so that all these numbers in modulus are equal to 1/2. So that means that so this is the amplitude. So then means that it's successful with a probability 1/4. So this idea, this nonlinear phase shift gate, it applies a phase shift of pi when there's 2 photons and does nothing when there's 0 photons or 1 photon. Okay, well, why do I want to do that? Well, it's because that's the basic element to do this controlled Z gate, which is also ingenious. So here I wrote what the controlled Z gate should do. So how did I write this here? Sorry. Yeah, so I don't know why I put 1 and 3 there. Ignore this 1 and 3 here. These are my, say, logical states of my photons, right? So this is in this encoding where I'm talking about, this should actually be 1 and 2, photon 1 and 2, and so on. So basically, I have my qubits defined such that I want to add a phase when both qubits are in the logical state 1. So here's what the logical basis in would look like, and here's what I want the logical basis out to look like. So I want to apply a -1 to this term here. So when I write this logical state in terms of this what's known as dual rail encoding, so here 0 and 1 are the Fock states. So if I have logical state 0, 0 for the 2 photons, that means photon 1 is in mode 2, and photon 2 is in mode, or qubit 1 is in mode 2, qubit 2 is a photon in mode 4, and so on. So Here I'm writing the photon number population for the 4 different modes, right? So here you can see that for these first 3 here, I want nothing to happen. And here I want to apply a pi phase shift. So what's the common characteristic of these first 3 here? It's when I have 0 photons in either mode 1 or mode 3, right? So here I have 0 photons in mode 1, and here I have 0 photons in mode 3. Here, also the same. So the only time I want to do anything is when I have 1 photon in mode 1 and 1 photon in mode 3, okay? So when, so when you look at this, right, you say, okay, well, what happens when I have this case of 0 photons in mode 1 or mode 3? Well, if 0 photons are in mode 1 and 3, that means the photons in mode 2 and 4, which basically means that the photons are going to propagate straight through here in modes 2 and 4, nothing happened, right? If I have 0 photons in mode 1 and 1 photon in mode 3, this photon comes in here, sees this beam splitter, it's going to split the amplitude. It's going to go sometime, it's going to go 50% amplitude up here, or 50% probability up here, 50% down here. And this nonlinear phase shift does nothing to the single photon state. So the photon just propagates through here, meets the other beam splitter, and exits to the same output port. And so basically, you can adjust the phase so that a single photon input into mode 3 here is always going to leave in mode 3. The same thing happens when there's a single photon in mode 1 and 0 photons in mode 3. The photon's going to propagate through here. It's going to see a standard Mach-Zehnder interferometer and leave here. The only thing that's going to happen differently is when I have 1 photon in mode 1 and 1 photon in mode 3. Here the photons are each going to meet at this 50-50 beam splitter. They're going to interfere. I'm going to have 2 photons going through the upper path or 2 photons through the lower path. I meet the nonlinear phase shift, which if it works, I'll apply a pi phase shift, either to this mode or to this mode. This phase shift is going to change the internal phase of the interferometer such that when the photons meet here, they're again going to split, but now they're going to split and carry this phase shift with them. So it's a global phase shift on the 2 photon component here. So so through the nonlinear phase shift, you're able to imprint this pi phase on the mode signature that you want. Yeah, so again, this works with, in order for this to work, I need both nonlinear phase shifts to work. Each are probabilistic, probably 1/4, gives me probably 1/16, but again, I can improve this with more complicated things using gate teleportation, right? So so this was kind of one of the first ideas about this back in, 25 years ago. More recently, this sort of idea has been extended to the whole kind of field, which is known as measurement-based quantum computation. And again, here, the idea is that you can produce some sort of entangled state. So here, I'm considering, say, each dot here is a different qubit, right? So a physical qubit. I'm going to entangle them using some operations. So maybe with these linear optics or however you want. Again, this is not particular to photonic systems, but you can do it in other systems as well. So these lines represent entanglement. So I'm going to create some sort of state here, right? So it's a multipartite state. And I'm going to prepare some state psi here, some state phi here, using the gates, which I know how to do, single qubit gates. And again, this entangled state is something I can produce. So my information, that's, say, sensitive information that I can't, say, manipulate or I don't want to destroy, are psi and phi, right? This is my resource, which I can prepare offline. So I can keep working until I prepared the entangled state, give me the psi and phi, I inject them into my system, and I start to work. And so the interesting thing here is then, so this shares the same characteristic with the teleportation-based scheme. You can move the difficult part offline and make it so it's no longer probabilistic and be close to deterministic. And so what you do here is you start applying measurements sequentially to your different qubits. And what you have to do is, based on each measurement result, you do some feed forward of the measurement result, so A here or lowercase a here. And then you do some second measurement on the next qubit, where the base is going to depend on what the first measurement was, and so on. So you do this kind of sequentially, and in the end, you can do this in such a way that the output result is equivalent to applying the unit, whatever unitary you wanted to apply, onto these 2 states here. And of course, this example is with just 2 inputs, but you can do this universally, so for any size computation. So this again, this is known as measurement-based quantum computation. It's interesting in the sense that the probabilistic nature of the information processing can all be done beforehand, and then you bring in your information once you have this entangled resource. This is also quite beautiful in the sense that you can see where the quantum nature of the whole game comes in, right? Because you need to make different entangled states with different kinds of topologies and so on. Of course, this is a very simple example, but if you look in the literature for more complicated things, you have the structure of these quantum states and so on, and different types of entanglement and so on. Another thing is that this can also be done sequentially. So, for example, here, in this example, I only really need to have, say, neighboring qubits prepared and entangled at a time. I don't necessarily need to have these last two qubits prepared when I'm doing these, so I can kind of be creating this as I'm going, and so there have been some experiments which have done this in the creation of this type of states. Okay, I have until 3:30, is that right? Okay. Okay, so I wanted to finish the last, say, 20 minutes or so talking about entanglement. So, in particular, photonic entanglement. So, as you know, a few years ago, the Nobel Prize was given for the experiments with entangled photons, violation of Bell inequalities, and pioneering quantum information science. So, I want to talk about SPDC, which is spontaneous parametric downconversion, which is something I worked on my master's, PhD, and to this day work on. It's one of the, say, workhorses of quantum information. So in terms of, say, quantum information technology, it's limited, but there's still many, many papers coming out improving SPDC, trying to make it scalable, putting it on chip, and things like this. So it's still quite relevant, even though I do believe that the single emitters, single photon emitters are kind of the future, right? But so what is SPDC? It's you have a linear coupling between a pump mode and your input modes and your output modes. It's a coherent quantum process. Meaning that you need to actually describe the quantum state produced. You actually need to use quantum mechanics, right? And something that's quite interesting, which I want to show you, is that how the properties of the output quantum state depend on, we'll say, the properties of the pump field, and also the type of material you're using, and so on. So you see this type of image describing SPDC. So you have your nonlinear medium, which is a crystal, typically. You have an input laser. It can be pulsed, can be continuous. It doesn't matter. It's intense. And so from this nonlinear coupling, so every once in a while, one of the photons in your laser is converted into this photon pair, which are the photon twins, or the downconverted photons. And this happens in such a way that one photon, say, leaves propagating in, say, this upper half plane, and this other photon leaves propagating in this lower half plane. You have, I don't know why, okay. I don't know why I have two frequencies there, but the point is energy and momentum are conserved in this process, basically. So, meaning that the sum of the frequencies of your downconverted photons are equal to the frequency of the photons in your pump laser, and also you have momentum conservation. So the sum of the k vectors of your two photons are equal to the k vector of your pump photons. And this, of course, this say correlation here, this classical correlation in this quantum process gives you entanglement. Actually, you can get really highly correlated quantum states, and so on. So you see lots of images of SPDC. There's different types. These are two of them, type 1 and type 2. So type 1, you have these light emitted in these cones. Green and red here are different, or these different cones are different frequencies of light emitted. So in type 1, you might have, say, a vertically polarized pump beam creating two horizontally polarized photons that satisfy conservation of energy and momentum. This is why you have this structure here. In type 2, it's a little bit more complicated. You have these cones that leave in, say, different directions. And here you can have situations such that, we'll say, a vertically polarized pump beam can produce one photon that's horizontally polarized, which might be on this green cone here, or leaving in this green emission cone. And then the other one could be vertically polarized, which would leave on this red emission cone. And then something which we'll see is that interesting things happen when you look at these intersection points of the cones, where you can find either horizontal or vertical polarization. But before we get into that, I want to show you this result, which was done at UFMG in Belo Horizonte in 1998, by Carlos Smoking, Sebastião Padua, and Paulo Souto Ribeiro. So I want to show you this because we're here in Brazil, and it's just such a beautiful result, and it's kind of the backbone of a lot of what is done with SBDC. I'm not going to show you many applications of this, maybe one in the second or third lecture, but something they discovered a long time ago was the following. So if you have this nonlinear crystal, if you put some sort of information in the pump beam, so here in their experiment back then, they put a mask. So just it actually was an F, it was a C. This is an illustration, right? They made a C, and they did this in such a way that they made the image of the pump beam, they formed the image of this mask here in this plane here. So you can see with this lens, as it's drawn here, I have the inverted image of the F in the mask appearing here in this detection plane. But here in the middle, this is the pump light, this blue light. So then what they did is they aligned this whole system to produce these down-converted photons. One photon went in direction here and was detected by detector 1. The other photon went in this direction and was detected by by detector 2. And they kept one detector fixed in one position, and they scanned the other detector in the plane. So they, literally used it as though it were a camera and went, went pixel by pixel, scanning around, getting the different counts, right? So when they looked at just the counts in detector 2, right, so the single counts, what you see is something like this. You see essentially a part of that emission cone, right? So you see, nothing really. Nothing that looks like an F at least. When you look in coincidence, so if I say, okay, I'm going to look at the events where I see a photon at detector 1 and detector 2 simultaneously. So detector 1 is fixed right here. I'm scanning detector 2. I'm doing the exact same experiment. I'm just going to take into account what happened to detector 1 also, whether it clicked or not. So if I take into account only the events where it clicks, I see the inverted image of the F here. So this is information from the pump beam that's being passed to the coincidence counts. The coincidence counts are the 2 photon counts, so right? So it only appears in the correlations of the photons, not in the photon 2 individually. Here, when you scan, you don't see anything. But if I say, okay, I'm going to condition which pixels I'm going to accept or which counts I'm going to accept based on what happened to detector 1, only when it clicks, I recover this image of this information that was put here in the pump beam. So they did this back then using this image. So for, I don't know, 25 years or so more, there have been tons of experiments using this type of effect to do, say, quantum state engineering. So what I've done a large part of my career is exactly this, trying to find interesting ways I can do something in the pump beam, pass this on to the 2 photon correlations, and study something interesting about the entanglement or whatever that appears. So it's a really cool way in which you can, say, engineer entangled states in these spatial correlations of the photons, right? And so this is something, there's a whole field known as quantum imaging, and so I call these quantum images because it's an image information that appears only in the correlations, right? Quantum imaging or quantum images corresponds to has other meanings as well, but here I think it's fair to use this term. Yeah, so you can do quite a bit with this, and a lot of, say, when you design SPD sources and you want to say, how can I couple the photons most efficiently into a fiber? What you do is you might put lenses here and basically focus the correlations onto the fibers, onto the cores of the fibers. How can I create states with more entanglement, less entanglement, so on? You do this type of thing. How do I destroy the spatial correlations so that I have really good polarization correlations and not spatial correlations? You manipulate the pump beam and you do some tricks here. So this is kind of a real backbone of what happens, or how you engineer these sources, not just for spatial correlations, but for others as well. Yeah, so one thing I want to mention in terms of these experiments is, so if you do like the most basic theory of SBDC, basically you can describe this process as a unitary operator, which would look something like this. You basically do a perturbative approach, and you have this expansion here. So here I wrote 3 terms down. The first term is when it's proportional to identity, so nothing happens in the process, which is what happens most of the time. I shine my laser in the crystal, nothing happens. The next term, here I have the destruction operator in the pump beam, and I have 2 creation operators, one in mode 1 and one in mode 2 of the 2 photons. So here I'm going to destroy one photon in the pump, create two photons, and that happens with some probability, or some coefficient rather. And then I have, the next term is actually this term squared, and so on. So this is what it looks like. You would then, so to see what happens, you could apply this to initial state. So I can assume that my pump beam is some classical field, right? I'm going to write it like this. And then I'm going to have vacuum in mode 1 and mode 2, where these operators here are going to act. And then the output state, ignoring the higher order terms, is something like this. So basically, you get a state where you have 0 photon, nothing happens, so you have 0 photons in mode 1 and 2, and that's with this amplitude here. And then you have 1 photon in mode 1, 1 photon in mode 2, and then you have these higher order terms, which typically can be good or bad depending on what you're trying to do. These coefficients are such that this one is very close to 1, and this one is, P2 is much less than P0. So as I mentioned, nothing happens most of the time, right? So, I mean, that's like not very motivating to say, well, I do my experiment 1,000,000 times, and one time something happened. That ends up not be so much of a problem. Of course, when you go, so it's bad when you want to make a pair of photons. It's even worse when you make 2 pairs or multiple pairs, or I think the record nowadays is 6 or 7 pairs of photons. So you have this coefficient to the whatever power. So it's very, very rare. So basically, if I were to look at this quantum state and kind of detect everything that comes out of my crystal, I would basically see this. I would see nothing, right? So this is where this coincidence counting and this post-selection comes in. So all the experiments you do with these types of sources, and this is something that's not particular necessarily to SBDC, but to other any sort of probabilistic source. If I have a fixed photon number that I'm working with, so I have n photons coming in from whatever source it is, I'm going to put this through some sort of optical circuit, whatever, which we've been discussing, and then I'm going to detect those n photons. And so so it really doesn't matter if I have losses, or sometimes the source doesn't work, or whatever what have you. If I say, okay, sometimes I produce n photons, and then I'm going to detect those n photons sometimes, I can basically only consider those events where I detected all n of them. And so these coincidence events not only remove this vacuum component in SBDC and other sources, but it also typically isolate or removes the higher order terms as well. So just to go back for a second. Yeah, when I have this state here, I might be doing an experiment where I really want to work with this term here. I want to work my 2 photons. But sometimes I might produce this guy here where I have 2 photons in each mode. And say if I detect one of the photons in mode 1 and another photon in mode 2, but that photon didn't correspond, isn't the brother or sister of the first one, then I'm not going to see correlations. So when I'm doing an experiment, I want to look at 2 photon correlations. Of course, I don't want to see, I want to see clicks, so I want to see at least this term, but then this ends up being kind of noise. So the lucky thing here is that this term is really less probable than this. And so, again, by doing this coincidence counting, I'm able to kind of isolate the event that I want to see. And this is essential for these experiments. This is the only reason you can do these single photon experiments, or even when you go to these single photon sources and so on. Of course, you want them to be as efficient as possible and so on, because you want it to work. But again, this isn't something that necessarily degrades the quality of what you're doing. It just makes it less efficient, typically. And so this is the idea of post-selection. So to finish, I just want to talk about, so I mentioned polarization in the beginning. How do you make polarization entanglement? You can take, there's several different ways. You can take 2 of these crystals, which I mentioned. You can make it so one crystal generates 2 horizontally polarized photons, whereas the other crystal could create 2 vertically polarized photons. I make a sandwich of them. And so in lowest order, I'm going to create a single pair, but I'm not going to know if it came from the first crystal with horizontal, horizontal, or the second crystal with vertical, vertical. And if I align this correctly such that I can't know, I'm going to have this coherent superposition here. So you can make this kind of this entangled state here, HH is plus VV, which can be close to a maximally entangled Bell state, or you can actually control the coefficients, which I didn't put here, but you can control them. So this was done a long time ago by well, so this two crystal source was here by Kwiat et al. In 1999, and it's quite robust and nice. This was another source where they used actually these intersection points of the two cones. So at the intersection points, again, you have one photon H, one photon V, or vice versa. You don't know which is which, and so you have entanglement. So both of these are really robust sources which were used for a long time. And nowadays you have, say, more efficient sources based on interferometers and periodically poled crystals and other devices, which maybe we'll get into a little bit in the next lecture. Okay, so another thing I wanted to mention here is, it's about 10 minutes. So now that we have these polarization tangled states, there's another thing I consider to do, which is actually a useful thing in photonic quantum information, is doing the Bell state measurement. So these are in the polarization language, these are the 4 Bell states. So the maximally entangled 2-qubit states in the polarization of 2 photons right here. So what you want to do in the Bell state measurement is to project into this basis, which is this entangled basis. So you want some sort of device that looks like this, where I send the photons in, and then one of these lights is going to turn on, telling me which of the 4 states I'm projecting onto. So this is ideally, a 4-dimensional projective measurement into this basis. And this is a primitive for entanglement swapping, teleportation, doing different quantum gates, some of the things which we've mentioned. Yeah, if you can write this out in terms of a quantum circuit and so on. So how do you do this with photons? So again, you go back to what we saw before with the 2-photon interference. So if I have 1 photon coming in mode A here, 1 in mode B, and suppose that now I'm going to write the Bell states in terms of the field operator. So instead of having HH plus or minus VV for these 2 states, I'm going to have the superposition of these products of the field operators applied to the vacuum state. So again, the game here is to propagate these field operators to the beam splitter and so on. And so I can do that in the same way I did a little while ago. So here I'm isolating, say, 2 of the Bell states. Later we'll see the other 2. So these components propagate like this through the beam splitter. And so because each photon, they're either both H or both V, they're going to interfere at the beam splitter, just like we saw. So that means that they're either both exiting here in mode A or both exiting here in, they're either both exiting, this AHBH goes to AHAH, BHBH, or in VV goes to AVAV, BVBV. And so when I consider now the coherent superposition of this, I see that these output states here propagate like this. So basically, I'm always going to see, for these 2 Bell states, I'm always going to see 2 photons in the same output port, either both of them here, both of them here, or both of them here, or both of them here, right? So I can't distinguish between the 2 of them, but they both have this kind of same detection signature. So if I put detectors here, I'm going to see 2 photons in one of the outputs and 0 in all of the other 3. But what happens now when I go to the other Bell state, the other 2 Bell states, psi plus or minus, where you have correlations HV plus or minus VH, I do the same calculation. I propagate the field operators through this device, and I see that when I have, so here's the transformations. Ignore these red circles; they might not be correct. When I do this all together here, basically, and I consider the coherent superposition of these terms, I'm going to see that the psi minus state goes to AHBV. So I'm always going to have 1 photon. Let's see if that. Yeah, so AHBV like this, so 1 photon in those 2 outputs, each of those 2 outputs, or 1 photon in those 2 outputs, which is the second term here. So I see that I have 1 photon on either side, right, 1 photon exiting one of the exits here of this beam splitter, and the other photon exiting one of the exits here in this beam splitter. When I consider the other state, I get this. So basically, I'm going to have 1 photon exiting one output port of this beam splitter, and the other one exiting the same beam splitter. Yeah, they're both in beam splitter in modes A or both in modes B. So basically, you can see that for the psi plus and minus states each have their own detection signature, and the 2 phi states have the same detection signature. So with this Bell state measurement here, I'm not able to distinguish all 4 of the Bell states like I wanted to, but with this simple device, I can project onto the psi minus state. In other words, I have unique detection signature for the psi minus state, a unique detection signature for the psi plus state, and then an ambiguous detection signature for the other two. So, and actually this is the best you can do with linear optics. There's several papers, theoretical papers showing that this is the best you can do. So, but it doesn't matter. So if you do, say, quantum teleportation, as you know, in quantum teleportation, you're going to do your Bell state measure with the 4 possible output results. Here, I'm only going to have 2 that are worth anything, right? The third result is ambiguous. I can basically throw it away and consider it as a case that the protocol didn't work, but I have 2 that worked. So it just makes your protocol probabilistic. So this is, I mentioned this because in say, building these quantum networks, and you want to entangle systems that are separated, which maybe we'll see in a minute or two, you want to, how do you entangle them? You make them emit photons, and you do a Bell state measurement. Right? So this is a basic mechanism for entangling distant quantum systems using basically the idea of entanglement swapping. Okay, I think I'm going to, let's see. Yeah, okay, I'll finish just making a few comments. So, so I'm here talking about photonic entanglement. I wanted to mention kind of what's kind of an interesting concept which we hear about maybe a little bit less. So in terms of entanglement and device independence, right? So when we talk about mixed states, right, we know that a bipart entangled state is, a bipartite state is entangled if I can't write it in this as this convex sum of product states here. So rho A and rho B are product states in systems A and B, and if I do this convex sum of them, if I can write the state like this, it's not entangled. If I can't, it's entangled. So for example, if I go to the Bell state, which I had before, I can write out what the density matrix is, and it doesn't matter what basis I use, it's always going to look something like this, which doesn't satisfy this relation up above. On the other hand, a classical correlation, this state here, you can see that I can easily write this as a convex sum of rows. This would be a row 0, 0, corresponding to 2 qubits in 0 state. This is a row 1, 1, 1, 2 qubits in the 1 state. So classical correlation is separable. You can write it in this convex sum. Another interesting case is this Werner state, which is a combination of the identity, so just kind of white noise, together with an entangled state. And this state, if you've heard about it or studied it, you probably used it to study, say, entanglement or other correlations. It's nice because depending on this parameter P, sometimes it's separable, sometimes it's entangled, so you can kind of look at this range and study how things go. It's also a state which models how, say, white noise would affect your system, and it's quite used. So when you talk about, this will be the last slide. When you talk about quantum correlations, we talk about entanglement, that's not the end of the story, right? So when here we're talking about quantum correlations, we're talking about, say, 2 qubits, and so I can define entanglement as being any state that is not this convex sum here, right? I mentioned when I showed the picture of the Nobel Prize winners, the Bell inequality violation. And so if you studied Bell inequalities, you know that in the formulation of Bell inequalities, at no point did John Bell use quantum physics to derive the Bell inequality. He considered, you have some systems that have some inputs and some outputs. And so in other words, without really planning on it, let's say, or how can I say this? His idea was to kind of refute physical theories, so he wanted, say, the least physical theory possible, so it's just a probability theory. He showed that, okay, if you consider some black boxes with some input-output characteristics and some real basic principles such as no signaling between them, you can show that you can derive an inequality that quantum mechanics violates, right? And so what you violate when you are violating the Bell inequality, you're showing that the correlations or the joint probability distribution which you measure here cannot be written as this convex sum here of individual probabilities on each system, right? So it's something very similar to the concept of entanglement, but instead of talking about density operators, I'm going to just talk about probabilities, right? So this is without getting too much into the weeds, this is the idea of the Bell inequality, right? And so you see the big difference between these. Conceptually, they're more or less the same. It's show that I have some correlations which cannot be written a certain way. And the difference between them is what I assume is going on inside my physical system here. So up above, I'm using all the formalism of quantum physics, writing density operators and so on. And down below, I'm kind of limiting myself to as little knowledge of what goes on as possible inside and between these black boxes. So there's also intermediate correlations, which is known as quantum steering, right? Which is a kind of a hybrid thing or an intermediate thing in which you have, say, a black box on one side and quantum physics or a quantum system on the other. And so you can write, again, you can define these correlations in terms of what they're not, right? So here you can say, okay, if I cannot write the system of the qubit here on side B as a convex sum of say, density operators with some probability which came from the other side, if I cannot do that, then I have some correlations which I'm going to call quantum steering, right? And you can, and so what's interesting here is that, and this will make me, sorry, that wasn't the last slide, the second last slide. So there's these form a kind of hierarchy. So you have, say, these are, say, the weakest or the easiest to produce, and this is, or to demonstrate, and this is the most difficult. So when you go to the Werner state, which I mentioned, it's really well known. So here I wrote a different Bell state, but it's the same concept. So this is the Werner state. And you can look at, okay, in function of this parameter P, what are the correlations? So if P is between 0 and 1/3, meaning that you have, very small component of the entangled part, the state's separable. I mean, if P is 0, all I have is identity, of course it's separable. If as I start increasing P, it's still separable. Starting with P equal to 1/3, I start to have entanglement in the state. And so as I increase the amount of singlet or the amount of Bell state here, it increases until I get to 1/√2, in which I can now start to actually see Bell inequality violation with this state, right? So I mean, so this shows that in terms of these correlations, entanglement and Bell inequality, you have this kind of hierarchy here, which is demonstrated here in the Werner state. And as it turns out, this quantum steering lies here in the middle, right? And so, in fact, as you change its parameter P, before you go from entanglement, just entanglement, you go to Bell inequality violation, you start to see this steering correlation in the middle. And so why am I telling you all this? Is because these, which we'll see at the beginning of the next lecture, is that these correlations can be linked to quantum information processing, in particular quantum communication and different types of protocols. And so I'll stop there because we're out of time. Thanks. I hope I wasn't supposed to stop 10 minutes early for questions.
No, but we have some time for some questions you have before going to the coffee break.
If you'd rather ask a question over
or
coffee,
you can
that's fine
ask
too.
the question during the coffee break.
Yeah.
That might.
Yeah.
Okay, great. So let's go to the coffee break.
Okay,
Thank you, Steve.